Newton's laws of motion. We're going to talk about the first law first. Makes sense, right? Well, the first law of motion is also known as the law of inertia. And before we go, we should really talk about what that word inertia means. Inertia is a resistance to change in motion. So when we say that inertia is a resistance to change in motion, what we're talking about is it's resisting changes to its velocity. When we talk about velocity, remember there were two things that we had to keep constant if we were going to have the same velocity. We had to keep the speed or the position versus time. We had to keep that constant, and we also had to keep the direction constant. So what inertia does is it resists changes to any type of motion. It's why when you change, like when, because I carry books around with me all the time, I put them in the seat. Well, I don't have cloth seats, and when I turn a corner, my books go flying off the seat. Well, it's inertia that's causing the books to fly off the seat. The books are trying to go in a straight line at a constant velocity, and when I turn the car, that's a force that's being applied that's wanting to change the motion of those books, but they don't want to change their motion, so they continue going straight. That's what we talk about with inertia. The other thing about inertia is that mass is a measure of inertia. The more mass you have, the greater resistance to change in motion. And that makes sense, because if you're driving a little bitty car, if you're driving a big semi-truck, it's a lot easier to stop the little bitty car from 60 miles per hour to 0 than it would be to stop the big semi from 60 miles per hour to 0. So the more mass you have, the greater your resistance to change in motion. How does that all play into Newton's first law? Well, Newton's first law, you guys probably learned it in middle school as an object in motion will remain in motion unless acted upon by an outside force, and an object at rest will remain at rest unless acted upon by an outside force. We learned about what motion really was, and so we can kind of take these two ideas and combine them into something a little more succinct, something a little bit briefer or shorter. An object at a constant velocity will remain at that constant velocity unless acted upon by a net force greater than 0. Now, the only thing that's really new in any of this would be net force, and we want to know what net force really means. Well, what a net force means, it means that we've taken all the forces that are acting on this object and we add them together. And when we add them together, we take into account positive and negative directions. Let's say we have two teams and they're going to play tug-of-war. And they're each pulling with 3 newtons of force. Now, if I did my free body diagram, this is what that would look like. Now, when I talk about the sum of all forces or the net force, both of those two things mean the same thing. It looks like this. We use a Greek symbol. That Greek symbol is sigma, and it's the same thing it means in Excel. So if you do Excel spreadsheets, it's the same thing. When you add up a column, you'll see in the formula line this little Greek symbol. This Greek symbol means add everything up. So when I say the sum of all forces, I would write it like that. And in this case, I have a positive 3 newtons and I have a negative 3 newtons. And when I add those together, I would get 0. To do another example of just what net force is, so you get an idea of what net forces are. Let's say they're pulling with 5 newtons of force. This is a stronger team. And they're pulling with 7 newtons of force. And in this case, my sum of all forces is equal to 5 newtons plus a negative 7 newtons. And that would give me a net force of a negative 2 newtons. That's what we're talking about. We're talking about net force. It means we took all the forces that are acting on an object and we added them together. The other thing is when we talk about net forces, and this is further down on this particular page, is that we look at forces in direction. We look at forces in the x direction or horizontally, what's happening that way, and we look at forces vertically, what's happening in the vertical direction. If we look at that, we could say that Newton's first law really talks about an object being in equilibrium. What conditions have to be met for an object to not accelerate, for its velocity to remain constant? In that case, we would say that the object would be in equilibrium. We have to look at both directions. We have to look at the x direction, in which all the forces would add up to equal 0, and if we did our sum of all forces, it would look like this. We would say sum of all forces in the x direction would equal 0. Or we would look at the sum of all forces in the y direction. And to write that, it would look like so. So what does all that really mean? Well, it means that when we do free body diagrams, such as a book on a desk, well, a book on a desk is in what state of motion? It's at a constant velocity, or a constant velocity of 0. So I would write that. We have our constant velocity of 0, and if we apply Newton's first law, what that means is, if that's my book, well, the book has weight. You can't get away from that. It's got mass, and gravity pulls down on that mass, so it has weight. The other thing would be the desk is pushing up. Now, the desk is pushing up exactly. Remember that's that normal force, that really super smart force that can adjust automatically? Well, the desk is pushing up exactly opposite the weight of the book. So I would have mg counteracted by the normal force. And if I added these together, these are all acting in the y direction. There are no horizontal forces. I would say n plus a negative mg, or n minus mg, would equal 0. I could also say n equals mg, because I could put the mg on the other side. So let's look at another example. Let's look at an example where we have forces in the x direction and forces in the y direction. So this time we're going to take a book and we're going to pull it across the table at a constant velocity. So there's my book. Now the book has weight, and I haven't really talked much about the difference between mass and weight because we tend to use those interchangeably. They are not interchangeable terms whatsoever. They mean two different things. If we look at mass, mass is basically the amount of stuff that makes something up. So we say amount of stuff. Number of atoms and molecules and how they're all put together, that's what the mass of the object is. Mass of the object remains constant. It doesn't change based on location. So we'd say remains constant despite location. Now, what is weight? Well, weight is different. Weight is gravity acting on that mass. It's a force. Mass is not a force. Weight is a force. Say that again. Mass is not a force. Weight is a force. Mass is measured in kilograms and grams, and in the English units it's measured in something called a slug. Weight is a force. Weight is measured in newtons, and if you want to do the English units, that's pounds. Weight is a force. Remember that. Weight is a force. You're going to be tested on that over and over, so make sure you get that cemented in your head. It's a force, and it is gravity acting on a mass. If I want to lose weight, I could go to the moon. And if I went to the moon, my weight would be 1/6 of what it is right now. I would instantaneously lose weight. I would have the same mass though. My mass didn't change, but my weight did, because the acceleration due to gravity on the moon is 1/6 of what it is on Earth. So if I want to lose weight, I gotta change my location. If I want to lose mass, I gotta get rid of atoms and molecules. So that's the big difference between mass and weight. So when we talk about weight, there's a formula to figure out weight. It's because it's a force. It's mass times gravity. That's equal to your weight. And that's why when we do free body diagrams, you see me put mg. Now I'll talk a little bit more about this when we get to Newton's second law. Let's go back. We're going to go back down to our example. We're going to pull a book at a constant velocity. When we pull the book at a constant velocity, that's your buzzword. If you see constant velocity, or the words at rest or stopped or not accelerating, all of those things tell you that all of your forces in that particular direction need to add up to equal 0. If my book is at a constant velocity, then I know that my forces should equal 0. Well, the book has weight, so go ahead and put that down, mg. And I also know there's that normal force that's acting on the book, pushing up with the exact equal and opposite, so that my sum of all forces in the y direction are the same as I had with my book on the desk. But in this particular instance, I am now pulling the book. So I'm going to pull the book. Now if that's all I put, then this thing would not be at a constant velocity. I have a net force greater than 0, so if I look at this net force greater than 0, I do have a net force greater than 0. Therefore, I would not have a constant velocity. But the parameters of this problem say I do have a constant velocity, which tells me that I have another force acting on this. And indeed I would. And that force would be the force that opposes motion, and that would be friction. My sum of all forces in the y direction look just like the book on the desk. But now I also have sum of all forces in the x direction, and that would be P plus a negative friction, or P minus F, equals 0, because it's at that constant velocity. Or I could put that friction on the other side and say P must equal friction. Okay, what I want you to do now, watch the video I've got for you on inertia.
Yeah, take it away, Ernie. It's going to be a bumpy ride.
What did you say your name was again?
I didn't.
Well, whereabouts are you headed?
The Leaky Cauldron. That's in London.
Do you hear that, Ern? The Leaky Cauldron, that's in London.
The Leaky Cauldron. Hey, if you have the pea soup, make sure you eat it before he eats you.
What, the muggles? Will they see us?
Muggles? They don't see nothing, do they?
No, but if you jab them with a fork, they feel. Ernie, little old lady at 12 o'clock. Ten, 9, 8, 7, 6, 5, 4, 3, 3 and a half, 2, 1 3/4. Yes!